Good morning, everyone, and welcome to week 2 of the CS3650 video lectures. Last week we introduced assembly language, and this week we're going to spend time on a bunch more assembly language concepts and examples. So the first thing that I want to do is start off with a coding example. We're going to go ahead and write a program that is going to average two integers. So create a file called average.S. For assembly, we can either use a lowercase s or capital S file extension. GCC is perfectly happy with either of those. The difference is that a capital S file extension goes through the C preprocessor, so we can use C-style comments, which is a little bit more convenient. So we're going to be using big S as our file extension. Like any assembly program, this assembly program is going to start off by saying global main, so that we can actually execute the program. It can find the main function where things start. Now we're going to have a data section and a text section. In the data section, I'm just going to go ahead and create a format string so we can print out the result. That's going to be a string that's going to say that the average of 7 and 3 is some number. For this program, we're going to be hard coding 7 and 3 as the input to our function. After our data section, we have a text section, which is where the code for our program goes. So we're going to start off with an average function. As we went over previously, every function that we're going to write in assembly starts off with a label, which is the name of the function, and then has an enter instruction, and then at the bottom we have a leave instruction and a ret instruction. Ret actually returns from the function. Enter and leave are bookkeeping that we'll talk about a little bit more later. Now, in a function in assembly, the convention is that the way we pass arguments to a function is in the argument registers. The argument registers are, in order, RDI, RSI, RDX, RCX, R8, and R9. So we have dedicated registers to pass up to 6 arguments. If a function has more than 6 arguments, they're passed by pushing them onto the stack. We'll talk about that more in a little while, but for now, 6 arguments should be enough for any of the functions that we're doing, at least in this example. Now, while we're talking about conventions, we also have return registers, and on Linux AMD 64, the primary return value from a function is stored in RAX. The convention actually allows for 2 different return registers. We can return a second value in RDX, but if we're talking about C programs, and mostly we're talking about how assembly code corresponds to C code. So if we're talking about C programs, there is no such thing as a second return value, a second integer return value from a function, so that's not really important. Our return register is RAX. So what that means is that this average function, so this average function is going to be the average of x and y is going to be equal to x plus y over 2. That's the function that we're going to implement. So this requires 2 arguments. So x is RDI, y is RSI, because x is the first argument, so it goes in the first argument register. Y is the second argument, so it goes in the second argument register. Once we have that, our plan for this function is pretty straightforward. We're going to add together our RDI and RSI. That's going to leave the addition result in the second argument there, RSI. And then we're actually going to move that over to RAX, because that's where we want it for the next step. Then we'll go ahead and we'll do our division, and then we will return that result, and the way we return it is by putting the result in RAX. So currently what this actually does is it just adds the numbers together and returns them, which is enough for our initial proof of concept test to see if this works. Then we need a main function. Again, this is a function, so enter 0, 0, leave ret. In here, we're going to go ahead and move 7 into RDI, move 3 into RSI, and then call our average function. So up here it said that the thing that we're going to be doing is printing out the average of 7 and 3 as produced by this average function. So here we're setting the first argument to be 7, the second argument to be 3, and then calling our function. After we do that, we're going to go ahead and move that format string into RDI. We're going to move our RAX register into RSI. So the second argument to the function we're about to call is going to be the result that we got back from the average function. We're going to move 0 to AL, and we're going to call printf. You'll remember that the reason we're moving 0 to AL is because printf is a function that takes a variable number of arguments, and so the calling convention that we're following requires that we specify the value 0 in the AL register before we call a variable argument function. So there's our program. That should be a complete assembly program. So you go gcc o average. We need to specify no pi, so it will compile, and then we can say average.s. We have an error on line 22. We need to move RSI to RAX. Someone would have caught that for me if this were a live class, but nobody can rescue me. I have to find my own errors. So now we'll run average, and it says the average of 7 and 3 is 10. So it's successfully doing the addition. All we need to do is this division. Now, to do division, we're going to use the idiv instruction. And the way the idiv instruction works is that it takes one argument. And that one argument, for now, is going to be the RDX register. What it's going to do is idiv divides RAX by its one argument. So implicitly, we're going to take RAX as the dividend. We're going to then explicitly specify RDX as the divisor. And so then we need to move 2 into RDX, because that's the value that we want to divide by. Conveniently, idiv puts its result in RAX, and everything should work great. Let's give this a go. Compile it, it works, run average, and we get a floating point exception. Now, we're not working with any floating point numbers, so getting a floating point exception here seems sort of odd. But this brings us to one of the sort of complications that we have with assembly in general, and especially with Intel assembly, and that is that some of these instructions are a little bit more complicated than you might anticipate at first, and so we really want to go ahead and understand exactly what the instruction does in order to be able to figure it out. So let me find a web browser here. I'm bad at finding web browsers. There we go. So here's our web browser. And we're going to go to the course site. At the course site, we're going to go to our AMD 64 assembly resources, and we're actually going to open up this file, the AMD Programmer's Manual Volume 3. And this AMD Programmer's Manual Volume 3 is the official documentation for what instructions are available on the AMD 64 architecture and what they do. So down here, we'll eventually find our list of instructions. We need to scroll through our list of instructions and find this idiv instruction that we're using, which is right here. It's on page 176. And what this thing says is that idiv divides the signed value in a register by the signed value in the specified register or memory location. All right, when dividing a word, the dividend is in the AX register. We're not dividing a word. A word is an old term that Intel used for a 16-bit value. So this is, you'll remember that we're talking about an architecture that started as the 16-bit 8086, became the 32-bit 386, and is now the 64-bit whatever processor you have. And so we have these terms. A word is 16-bit. A double word is 32-bit, a quad word is 64-bit, and then a double quad word is going to be 128-bit. Now we're trying to work with 64-bit values, And so that means we're going to end up with this final variant where we're dealing with R registers. We're on AMD 64, so the registers that we're interested in are registers like RAX and RDX. So what this thing actually does is it's going to divide a double quad word by a quad word. That's interesting. A double quad word is 128 bits, and 128 bits doesn't fit in a single register. So in order to have that value, it actually specifies that that lives in two registers. The high 64 bits of the number are in RDX, and the low 64 bits of the number are in RAX. Now we're just trying to do an integer division, so we're not really interested in being able to represent a 128-bit value. So what we want to do is make sure that the high bits are 0, and then we will successfully divide the low bits in RAX by the register that we specify in the second thing. Further, it says here that when it's done, it's going to put the quotient in RAX. We knew that. But then it's going to put the remainder in RDX. Interesting. So if we had some value in RDX, it's getting overwritten. Given all this information, let's go ahead and try to fix our program so that it actually works. So the first thing is we probably don't want to use RDX for anything, because RDX is part of the input. So instead of using RDX, we're going to use a safer register. We can be pretty sure that like R10 isn't being used for anything. Intel never heard of R10. It didn't exist on the 8086 or the 8386, so it's not going to have any special meaning. Now, we're going to divide by R10. So that's solving the problem of the register that we chose conflicting with the register that the instructions are going to use. But we need to make sure that the value in RDX for those top 64 bits is 0 before we do the division. Because right now we have no idea what's in RDX. So it gives us this hint back in the manual, and that says, to avoid overflow problems, precede this instruction with a CBW, CDQ, CDO, or CQO instruction to sign extend the dividend. So what that's going to do is if the number in RAX is a positive number, it's going to put 0 in RDX. And if the number in RAX is a negative number, it's going to sign extend that number. So it's going to put all 1 bits, because we're dealing with 2's complement numbers, into RDX, which gives us the behavior that we want. So that is CQO is the instruction that we want. Once we've done that, we can give this another try. And we find out that the average of 7 and 3 is 5. Now you might have the question, why did we get a floating point exception dealing with integers? We can actually find that out here. It says one of the possible exceptions is that we can get this divide by 0 exception, which the Linux C+ or C runtime is going to spit out as a floating point exception, just because that's how historically that usually was, and it never actually gives us error messages that are really what the error was in this sort of situation where things break. In any case, this was this wasn't either. This was the result of an overflow. We would get the same result from divide by 0. So there is an example that shows function calls, and this example also shows the fact that some of the instructions on AMD 64 are weird, and therefore when you're dealing with something like idiv that has implicit arguments, or might have multiple outputs, or might for some reason take a especially large input, what you need to do is go find the documentation, which for instructions is this AMD Architecture Programmer's Manual Volume 3, and actually go read the documentation, because that helps. I think the last question that we have here would be, why does idiv take a 128-bit dividend? And the answer is pretty simple. And that is because if we do a 64-bit by 64-bit multiplication, that produces a 128-bit product. If we go look at the imul instruction, which is going to be under imul, we can see that it's going to store the product in rdx::rax. So if we multiply together two 64-bit numbers, we're going to get a 128-bit number stored in exactly the same place that idiv expects to find its dividend. And so that means we can have multiplications and divisions of relatively large numbers. We can do a multiplication and then reverse it with a division, which is sort of elegant, and that's all wonderfully useful. This is sort of interesting as an example of something that isn't exposed in most programming languages that are higher level than assembly. If you want to do this 128-bit division or 128-bit result from multiplication, you may have to actually write assembly code, but it is something that the hardware supports. All right, so that's our first example. I'll be back in a second with the thing that we're doing next.